Hey everyone, in this video we're going to be talking about rolling contact bearings and specifically looking at bearing survival. This video is part of a lecture series on mechanical design 2. So what we're going to do in this lecture is go over what happens if we have a change in reliability goal. So far in the first video in this module, what we looked at was everything for a certain reliability and for a certain force requirement on our bearing, but we haven't looked at what happens if we want a higher or lower reliability. And one thing that we have to start with is, a question that we have to start with is, how do we define our statistics of failure? And essentially what we can do is we can look at a graph of failures versus life of a bearing. So let's say we do a lot of different experiments and we start plotting for a certain bearing how many failures we get and at what point we get the failures. And then we can sort of create some sort of bell curve to write this. Now, typically you would assume that there would be a normal distribution of failure in your chart, so that essentially the failures could look something like this, and I'll draw it and then I'll erase it. So a normal distribution would look something like this, with the maximum of failures happening at a certain life, and then with we know our 10% of failure rate would be somewhere at the beginning there, and then we're going to design so that we can say that the life rated of our system would be at 10% failure or 90% reliability. So this would be our L10 or our reliability design at 0.9 essentially. So this is actually not the case in real life. So in real life, we actually have a different distribution. And I'm going to erase all of this just so that we can redraw it for the actual real life skewness. But in real life, the failure modes look more like this. So they look much more skewed to the right. So we can say that there's a right skew. And because there is a right skew, we need to come up with an equation for reliability that fits the curve for reliability. And so our 10% might occur somewhere here. So our L10 or life, where 10% of our failures happen, might be a little more to the right than we initially expect. And so what we're going to do is we're going to develop some equations associated with this. And instead of using a normal distribution equation curve, we're going to use what we call the Weibull method. And what the Weibull method does is it allows us to essentially plot, curve fit a failure mode graph with a certain equation. And so we can come up with that the equation, and this is copied from your textbook in order to make it easier to read. We can see that the equation would be R is the exponent of x minus x0 divided by theta minus x0. Okay, all to the power of b. Now, these three parameters are x0 is a guaranteed or a minimum of minimum value of x. So it means it's essentially where the first, so this would be the value of x, okay? This is where the first failure would occur. Now, x is not in terms of L. X is a little bit different. X is called the life measure. Okay, and what the life measure is just L over L10. So instead of drawing a graph of failures versus L, what we would do is do a graph of failures versus X, okay, where X is L over L10. And we know that L10 is usually 10 to the 6 revolutions, okay? It's our usual life that we have occur, life rated, which is usually 10 to the 6 revolutions. So it's just a way of redrawing the graph in terms of X. Okay, so this equation is in terms of x, where x0 is essentially the guaranteed value of x. So it's the lowest value of x that you will always have. Okay, it's a guaranteed value. Now, theta is a characteristic parameter. So this characteristic parameter is how much skewness there is in the graph. So here we see that we have 63.212 percentile of x for rolling contact bearing. So that means that there's a certain skewness associated with the graph within the equation. And then b is a shape parameter that also controls the skewness, and for rolling contact bearings, that's equal to 1.5. So we have all of these different terms, and now we can start thinking of how we would solve the problem. So let's think of let's think of how we would actually use this graph to make sure that we work at it correctly. So let's say we are given a problem where we have a given reliability, and this reliability is other than 0.9. If the reliability is 0.9, we have already methodologies in the first video that we're able to, in first video of module 3, that would be able to solve the problem. Now, if we're given a different reliability, then what we can say is that L desired, we're going to have a life desired over LR is going to be equal to X. And we know that our life desired might be at a different reliability than originally, or a different reliability than 90%. So for example, we could have an R of usually greater than 0.9. So usually we're going to go with an R that's greater than 0.9, because in real life, we don't want to have 10% of failures occurring because we chose a bearing. We actually want to have usually 95 or 99% of failure. It's 99% of resistance to failure. So what we can do though is, if we have LD over LR, what we can say is we can find what our value of X is given a reliability. So we can find what the value of X should be, or what the life desired should be, if we increase our reliability from 0.9 to something else. And this would be given by rearranging this top equation. So if we take this top equation and we bring it down here, we can rearrange it, and we can say that if we actually rearrange it to find X, we can say that X is going to be equal to X0 plus theta minus X0, all in brackets, times the natural log of 1 over R to the power of 1 over B. Okay, so just rearranging the equation. Now, you don't really need to know how this happens. If you want, there's more information in your textbook on Weibull parameters and how we can rearrange this equation. But essentially, this gives us the life desired that we can have based on a reliability that we can find for a certain bearing. Now, this is just a useful equation to have if we need it, okay? All of the stuff that we're doing in the first lecture and the second lecture, or these first two videos, is building up to being able to solve some examples and creating a set of equations that we can then use to solve problems. Now, typically the problems that we have are going to be the following. So let's say, so far we've learned that manufacturers test at a value of C10. So that means that they test at a reliability of 0.9, and they give you the value of C10, which is F rated at a life rated of 10 to the 6 revolutions. So what the manufacturers do is they test and they find the force rated, or the C10, at 90% reliability when the life of the system is 10 to the 6 revs. Now, in real life, when you're picking a bearing, your desired load is probably not going to be equal to your manufacturer test load. Okay, so I'll just put manufacturers. It's not going to be equal to the manufacturer's test load. So you're going to have to find a bearing with a potential different force or a different force desired than what the force rated was. You're also going to have a different speed potentially, so a different rotation or a different amount of revolutions. You're also going to have a different reliability. Typically, your expectation is to have a higher reliability than 90%. Okay, we want to have a reliability that's much higher than 90% for our system. So the expectation is usually that R should be greater than 0.9. We'll never have a system where you're actually looking for a reliability that's lower than 0.9. That probably wouldn't happen. And so what we can do is we can take our log of F versus our log of life curve, and instead of writing log of F versus log of life, what we're going to do is we're going to call this log of F versus log of X, okay, where X is just life over life 10, okay, or the life rated essentially, okay. And what we're going to do here is we're going to start drawing a system of equations. So what we know is that currently when we have a log graph like this, we have a point, for example, here where the manufacturer tests at a reliability of 0.9. So this line is for a reliability of 0.9. We have a straight relation between F and L in a log format, and we can say that this would be the manufacturer testing at C10 and manufacturing at X is equal to 1, which means they're essentially manufacturing at life 10, okay? So this X is equal to 1 would just be L10 over L10, or we can also write this as LR over LR, okay? It's the rated reliability, okay? And that's equal to 1, okay? Now, based on that, we now then have us as a as a desire for our design. We actually have a force desired that is different, and we're trying to figure out also based on our life desired where we have to go. So for example, we would have a force desired and a life desired that could be lower, and as a function of that, our force desired could be lower as well, okay? We don't really know how much that is, but we also know that our reliability desired is going to be higher. So our RD is going to be greater than 0.9, okay? And so what we can do here is we can draw a new line that's going to intersect this new system. And this new line is for an R desired of greater than 0.9. So whenever you have a desired reliability that's higher than 0.9, you are automatically shifting your graph towards downwards, essentially, because the force that you desire for a higher reliability has to be lower than your initial C10. And in order to get to that point, we can call this point D, and we'll see in a second why. We need to get to either here or here and then move along the line. So what we need to do is we need to get to a point, either point B or point C, and then from point B or point C we can then go towards. So we have these two paths that we can take to get to this new reliability based on the original bearing. So let's write some building equations based on this. So if we look at this graph, and what I'm going to do is I'm going to copy over a clean version of the graph as well. So in our notes, we also have a clean version of this graph so that we can clearly see what's happening. Okay, and we can see that the graph is slightly different because it has a desire that's higher than the current life, so it looks a little bit different. Okay, so you can see that my point D was actually somewhere here, whereas the point D in this graph is actually towards the right, but it follows exactly the same thing. So your x desired is further that way, okay? It's further than x10, and our FD is lower than C10, just like before. So our original graph had it so that the point was here, but it actually comes out to the same thing. So if we go from, let's say that we look at line AB, okay? So what we can say is that along a constant load line, AB, then on our constant load line AB, we have a constant load of C10. Okay, so to get from A to B, we have the same exact load happening at A and B, it's C10. Okay, however, if we move towards the left in our graph, so if we go from point A to point B, what we're actually doing is we have, in order to increase our reliability, which is our reliability desired, we're actually reducing our life, okay? So our life gets reduced, okay? Or our life desired has to be reduced, okay? So if we want to keep the same force on our bearing and we want to increase the reliability, we have to reduce its life, okay? That makes complete sense. And we can call this LB because this is not our life desired. This is just a midpoint problem where we have a life. If we were to use the same force, then we know we would have a life that would be reduced. And in order to increase our life, what we need to do is we need to essentially reduce our force again, okay? So in order to move from point A to point B, we need to use a constant force, and therefore we have a lower life. And then in order to increase the life, we can then go from point B all the way to point D. And in order to get to point D, what we need to do is we need to reduce the force until we get the life that we desire, or the XD that we desire. So what we can write is that an equation that's valid along the constant load line is that RD is equal to the exponent of minus, so if I go back to my equation for R, we have that this is minus XB minus X0 over theta minus X0 all to the power of B, and all in brackets. Okay, based on that, if we know our value of XB, we can find RD. We can then say, okay, my reliability desired is this much, so now I can find what my XB would be to shift what my LB would be essentially, or what my XB would be. Okay, they're equivalent things, they're just one is divided by L10. So I can rearrange this equation to say, just like we did before, I can say that XB is equal to X0 plus theta minus X0 ln of 1 over RD to the power of 1 over B, and that will give us our value of XB, which can then be translated, if we know L10, can be translated to LB. So we can find our life at point B. Then based on that, once we know our life at point B, mathematically what we can do, what we're going to do on the graph to get from point B so if we want to get from point B to point D, what we can do on our graph is we can say, well, we can move along our line of constant reliability, okay, which we've done in the previous lecture or in the previous video as well. So we can say that on that line, we can say that FB LB to the 1 over A is equal to FD LD to the 1 over A, okay? If we look back at our previous lecture and our previous video really quickly, we can see that we had this exact same scenario here where we came up with the fact that if FL to the 1 over A is constant and essentially the reliability is constant, then we have this equation. So that's what we're using as we go. And we can say that as desired life goes up, force has to go down. Okay, so we're following the exact same pattern as before. So then what we can say is well, I'm going to rearrange my equation in terms of FB. So I can say that FB is equal to FD times LD over LB to the power of 1 over A. And I know that my FB is also equal to C10. Okay, based on my graph, I know that my C10 is this. Now, I can also write that this is also equivalent to XD over XB. So I can substitute into my equation and say that LD over LB is equal to XD over XB. And there's no real reason to do this, but it's a good practice to do this because it makes it a little bit easier to solve our problems, because of the fact that now what we can do is I can say that if I want to go look for a catalog number based on a force desired, I can say that my C10 is equal to FB, okay, that's my force at point B, and that's going to be equal to my force desired. So if I have a certain force desired, I can go look for this catalog number through this force desired, okay? And what I'm going to do is force desired multiplied by my XD over XB to the power of 1 over A. Now my XD over XB is not just going to be XD over XB, because XB is hard to find. So what I'm going to do is I'm going to substitute in my XB equation right here. I'm going to substitute that in to my equation down here. So I'm going to have that this is equal to XD all divided by X0 plus theta minus X0 times ln of 1 over RD to the power of 1 over B. Okay, and this gives me an equation that I now can use to solve a problem with a different reliability than my original requested reliability, and I can find my catalog number from it. So if my reliability is at a reliability of 0.9, it makes it very easy. I can use the simplest equation to find C10. If my reliability is different than 0.9, I can now use and plug in this equation to find my catalog number for a bearing where I know what my, so you would solve a problem like this where your known would be FD, LD, and RD. So if you know FD, LD, RD, you can find C10, and then you can go to catalog and you can find a matching bearing to the conditions that you need. Okay, hopefully this makes sense, and if it doesn't make complete sense, it will in the next video, because in the next video we're going to do some example problems associated with this problem, with this equation and bearing survival. So this equation above can be used for any reliability. Okay, so at any reliability you can use this equation. You can even use this equation for 0.9. Now, if you plug in for 0.9, you'll find out that you just have FD times XD to the 1 over A. So you'll be doing some extra work, but it's something that you can definitely do if you want to. Okay, so you could use it for every single case for any reliability. Now, for 0.9, we have a specific equation that we can use, and we'll show you that in a second in our formula sheet for this module 3. And we're going to find a slightly simplified equation that we can use for reliability is greater than 0.9, just because we can get away with a slight simplification of the equation, especially if you're not using a calculator. Okay, So one more thing that we're going to do to this equation is we're going to add what we call an application factor. So I'm going to call this A sub f. And A sub f is an application factor. And what this application factor is it is pretty much just a safety factor that we apply to our equation. So it's AF multiplied by everything else. Okay? So multiplied by everything else being FD times the whole bracket here that I'm not going to repeat to the power of 1 over A. Okay? Now, if not given, you can just say that your application factor is equal to 1. So if it's not given, you can just say it's equal to 1. I'll put if not given, that way you have it, and we can go from there. Now, another simplification that we can do is that ln to the 1 over rd in our bottom part of our bracketed area, so in this one right here, okay, ln of 1 over rd, for r is equal to or r is greater than 0.9, what you can say is that this ln over r ln to the power of 1, ln of 1 over rd can be equal to 1 minus rd. And this is usually the case once reliability comes really close to 1. Okay, so if you have 0.99 or 0.98, ln of 1 over rd is going to be very similar to 1 minus rd. Okay, so you can simplify and plug into your equation your 1 minus rd. And now what we're going to do is we're going to look at our formula sheet and see where all these equations are located in our formula sheet so that we can then go into the next video and start solving real problems. Okay, so if we go to our Module 3 formula sheet, you'll see that in the middle here we have that we know that this is the first relation that we developed. Then this is a conversion between life in hours and RPM to a life in revolutions. Okay, and we have this conversion right here as well. And here we can see that C10 is equal to FR, which is your C10 is what you're looking for in your catalog, is equal to FD, or force desired, LD over LR to the power of 1 over A. And just to simplify this, you can also write it in the terms written right here with your life in hours and your ND in revolutions per minute. And you can see that this equation is valid for R is equal to 0.9. So if you don't have a change in reliability, you can just use this equation for R is equal to 0.9, and it just makes it a lot simpler, where LR is equal to 10 to the 6th. Now, what we've developed in this video is we said that C10, and this is valid for any reliability, is going to be equal to AF times F of D, open brackets, X of D over X0 plus theta minus X0, ln of 1 over RD. So this would be our more complex equation where R is equal to any reliability desired that's other than 0.9. And then for simplicity purposes, if you're doing an example and you have a problem with that example or something is going on and you can't figure it out, another equation that can be used is RD is greater than or equal to 0.9. You can also simplify your ln of 1 over RD to 1 minus RD, which makes it a little bit easier to solve the problem. Okay, then we'll look at some reliability equations as well. So these reliability equations, we've already written those down in some way. These are just different notations of that reliability and working with that equation to bring it into different formats, but we'll talk about that later on. So for now, all that we need to know for the next video is we need to know our equations so that we can use them to solve some problems that we'll look at in the next video. So we'll see you in the next video for that.